All right, thanks everyone for being here. My name is Fermi, and I'll be talking about pseudorandom unitaries and compressed purifications. I'll say what both of these mean during the talk, so don't worry. This is joint work with Robert Huang, who's here in the back. Right, so the basic question that we'll be answering in this talk is the following. Can an efficient quantum circuit look random? And what I mean by this question is the following. When I say an efficient circuit, I don't mean any particular fixed circuit. I mean a family of circuits or a set of circuits. So this is a set of circuits on n qubits. And I'll call them a set of circuits on n qubits, u sub k. So the circuits are indexed by some index lowercase k. And these are polynomial size, a poly in n size efficient quantum circuits. So that's on one side. And the question is whether you can have such a family of efficient circuits that are, yes?
Are they required to depend uniformly on n in some sense?
Doesn't matter, let's say.
Can you pick independently for each n?
Let's say it doesn't matter, yeah. And the question is whether these circuits can look indistinguishable from a Haar random unitary. Let's say they're not uniform. Like for every n, you can pick a different family of circuits.
Independently for each n.
Sure. I think it'll be more clear later on when we see what the circuits look like. But okay, and so the question is whether you can have an efficient family of circuits that looks indistinguishable from a Haar random unitary. And by looks indistinguishable, what I mean is that from the point of view of any efficient quantum algorithm, A, so this is an algorithm here. It's a polynomial time quantum algorithm, meaning that it has a polynomial number of gates, acts on a polynomial number of wires. And I'm writing A to the U to denote that this algorithm has access to U as an oracle. So it has access to these special gates that are going to apply the unitary U. And once you fix like any particular polynomial time quantum algorithm of this form, what's going to happen is either you're going to instantiate this U by sampling it at random from this family of circuits, or you're going to sample U as a Haar random unitary. And the algorithm's goal is to decide which distribution you sample from. And what we'd like is that for any polynomial time quantum algorithm, it can't distinguish these except with some negligible probability. Okay. And I'll be calling this algorithm an adversary because we'll think of it as, this is sort of a worst case quantum algorithm. It's trying its hardest to try to distinguish these two distributions. So such a family of circuits is called a pseudorandom unitary, or PRU for short. And this was introduced in the seminal work of Ji, Liu, and Song in 2018. Okay. Any questions on the definition? We're going to be. Yes.
Need to be in that circuit.
Yeah. Algorithm, it has oracle access to U. So you can query it in sort of any way it wants. The only restrictions are because it's polynomial time, the number of U's in this picture is going to be polynomial. But yeah, it's the same U at every step. Yeah, just say that at the end, the algorithm is going to measure some bit and then guess whether it's seeing the pseudorandom world or the random world. And we want to say that for any quantum algorithm, the probability it guesses, the probability outputs 1, let's say, is close in both settings. Good. So for those of you who've seen the notion of a design, like a unitary T design looks like very, very similar to this notion. I guess there's two real differences, though. One is that in a T design, the number of queries you can make to the U is sort of bounded a priori. Like you fix a particular T that you fix a particular parameter T, and then you have a construction that is fixed for this T, and you are indistinguishable against Haar random unitaries up to T queries. I think it's actually like T like parallel queries, not even like T adaptive queries like what this can be. And the other is that a T design is a statistical notion, meaning that like it needs to look indistinguishable from a Haar random unitary from the point of view of any quantum algorithm, like not just efficient ones. Whereas here, I'm only going to ask for this to be secure against an efficient quantum algorithm. And that's kind of how you're able to like not impose any a priori bound on T. Does that make sense?
I guess here can also be poly n, but then
So that one.
The T here is that fixed.
So this is like you fix a particular construction in advance, and then later any polynomial time quantum adversary can come by, and whatever polynomial it picks, you'll fool it. So in some ways, like it's like if you only care about computational guarantees, it's like much better than a T design. Right? Sorry.
Is podium in both space and time?
Yeah, just think of A as efficient. So it's efficient, you count these U gates as like cost 1. And so just whatever rules you would apply to say like a circuit is polynomial time, you would apply to this. Or polynomial size, yeah.
Each time you query, do you get the same unitary or a different unitary?
You get the same unitary. Yeah, it's like there's like a magic box that implements a particular unitary. And you get to go and like use this box as much as you want, as long as you're an efficient adversary. And you're just trying to decide like, was I given a box that was sampled from this distribution or the other distribution? But like once it's sampled, it is fixed for all time, and I'm just trying to decide which one I was given.
Your top diagram is the same.
It is the same, yes. Yeah. All right, this is great. Any other questions? This is like the whole talk kind of depends on this slide making sense, so this is great.
So is there a magnitude, is the order of a limit between T and N? Say you can have like how large numbers of 18 you can.
So N is going to be the number of qubits the unitary one. Yeah. And when I say that something is polynomial, I want it to be polynomial in N. And so when I say that A is efficient, that means that one consequence of me requiring that A is efficient is that T is going to be polynomial in N. Yeah. Just because A is efficient, so right. Anything else? Okay, so yeah, why study pseudorandom unitaries? I think like honestly the reason that I'm most attracted to this problem is just because it's mathematically a very elegant, simple question, quite natural. But if you don't buy that, there are a bunch of applications of pseudorandom unitaries to various domains. So I think the area in which they've attracted the most attention is in physics, where pseudorandom unitaries, in essence, they allow you to model physical systems, like physical processes, as sort of behaving like a Haar-random unitary. So this is like a common kind of heuristic thing people do when studying like black hole information scrambling. They pretend that like the evolution of a black hole corresponds to a Haar-random unitary in some sense, and then derive various consequences, like making this heuristic assumption. But on the other hand, if something corresponds to like a real physical process, and you believe the quantum extended Church-Turing thesis, which says that like, basically every physical process can be simulated efficiently on a quantum computer, then it's sort of inaccurate there's this tension here where you'd like to pretend, or you'd like to model this physical process as behaving like a Haar-random unitary, and yet you know, because it's a physical process, it can't be, and Haar-random unitaries are exponentially complex. You kind of can't have both of these at the same time. And pseudorandom unitaries give you a way to sort of resolve this tension and say that at least if you only care about like the computational consequences or like the efficiently detectable consequences, there is actually, or if pseudorandom unitaries exist, then there is a way to actually instantiate unitaries that behave like Haar-random but are also efficient. Pseudorandom unitaries also, they're originally like from the field of cryptography, and the motivation there was that these are just a natural quantum analog of a fundamental cryptographic object called a pseudorandom function. So that's a crypto object that is used sort of everywhere. It's used to like build encryption schemes, and pseudorandom unitaries in quantum cryptography can be used to build quantum encryption schemes. So encryption schemes that run on quantum computers. There's also implications in other areas such as quantum algorithms and learning. So for instance, if you construct like a low depth pseudorandom unitary, then like the existence of this object has implications for how hard it is to learn like circuits of a certain depth. Because if an object looks like it's a Haar-random unitary, then you shouldn't be able to learn it intuitively. And finally, one thing I'll talk about today is that by studying pseudorandom unitaries, we'll be able to get like new perspectives on just truly random unitaries themselves. Okay, so until this work, it's been an open question to actually show that pseudorandom unitaries exist under reasonable cryptographic assumptions. And in the last couple of years, there's been quite a lot of progress, which has gotten us closer and closer to answering this question. But all these prior works still have gotten stuck at constructing PRUs, but only ones that are secure against highly restricted families of adversaries. Okay. So for instance, like the general model of an adversary that can query the unitary any polynomial number of times, that's not something that we could handle in prior work. However, we could handle we could handle it if you assume that the adversary queried the unitary in like a certain way. For instance, all of its queries were made at exactly the same time in parallel. Okay, so what makes it tricky to reason about PRUs, to construct this object? It's always hard to say why something is difficult, but let me just try to give some like rough intuition for what makes the problem look a little scary. So what we're trying to understand is this state here. So this is I'm going to denote ket AU to be the state of the adversary after its queries after it makes its T queries to this particular unitary U. And your goal, when you construct a pseudorandom unitary, is you have to prove some sort of indistinguishability statement here. You need to show that there's two mixed states, one being the mixed state that you get when the adversary is instantiated with a unitary drawn from the PRU ensemble. And the other is this mixed state that the adversary has at the end when the unitary is drawn as a Haar-random unitary. And you need to show that these two mixed states are indistinguishable. And already, like, the typical way that we think about expressions like this, like just the right-hand side, is using something called the Weingarten calculus from representation theory. So this is a I guess powerful set of tools that let you compute low moments of random unitaries. And so you can look up expressions like this. These are like what these expressions look like, even just for order or degree 2 terms. And using these fairly scary expressions, you can compute individual entries of the matrix on the right-hand side. And honestly, sort of the complexity of thinking about the problem this way has been maybe the source of the difficulty, in that we know techniques to compute individual entries of this matrix. Those techniques are sort of unwieldy. And yet, that's not even the end goal. The end goal is not to compute the exact entries here. It's to show that these two density matrices are close in some sense. So we kind of lack the mathematical techniques to get a handle on statements like this. So in this work that I'm talking about today, joint with Robert Huang, we have the first provably secure pseudorandom unitaries. And actually, we achieve two different notions. The first is the standard notion that I've described today, where the adversary is given the ability to query the unitary U. And I'll talk more about what the particular construction is later. But just to kind of give you a taste of what the construction looks like, the construction is of this form. It's going to be the pseudorandom unitary family is going to be a random n-cubic Clifford times a random classical function implemented in the phase times a random permutation implemented in place. So if you didn't catch that, don't worry. I'm going to spend quite a bit of this talk actually diving into the particulars of this construction. And the second notion of a pseudorandom unitary that we construct is we call a strong PRU. So this is a strengthening of the original definition of a pseudorandom unitary, where I give the adversary the ability to not just query the unitary in the forward direction, but also the inverse direction. So it can query, it has two oracles. One is an oracle for U, one is an oracle for U dagger. And this gives it further insight into how this unitary works. And for this, we actually have to change the construction. We have to throw one more Clifford on the other side of the construction. But we show that both of these notions can be instantiated under reasonable cryptographic assumptions, namely that a one-way function exists. Okay. And one can argue that for a lot of the applications of pseudorandom unitaries, it's actually more reasonable to assume that your attacker has access to both the forward and backwards direction. Despite that, I'm just going to focus on the first notion for this talk. And a lot of these ideas sort of like give the foundations for how we prove the second result. Okay. Any questions at this point? And the main idea behind how we get these results is something I'll call compressed purifications, which is a completely elementary method to analyze random unitaries. Actually, the slide is a little bit wrong. This technique is not just for random unitaries, but at least for this work, we're going to use this technique to analyze random unitaries. And this has a bunch of other applications that we show in this work. So one other application beyond just pseudo-random unitaries is that this compressed purification technique gives a way to just reason about random matrices in general. So what we show is that under fairly mild conditions, namely you want these random variables to be bounded and mean 0, we show that any matrix with IID random entries looks like a Haar random unitary. And by looks like, what I mean is that if you imagine a quantum query algorithm, and you literally apply these matrices to the state of the algorithm, the resulting density matrix would be close, whether you instantiate it from one of these distributions or as a Haar random unitary. So for instance, we show that if you were making queries to a random ±1 matrix appropriately normalized, or even a random sparse matrix, this can look indistinguishable from a Haar random unitary. I just want to mention, when we have these matrices with IID entries, they are not necessarily unitary, so this is not entirely physical. But this is a well-formed mathematical statement about closeness of density operators. Another application of this compressed purification framework is it helps us reason about low-depth random circuits or low-depth PRUs. So on this front, there are no new end results. There's a recent work of Schuster, Haferkamp, and Huang that constructed or gave a compiler for how you turn any pseudorandom unitary construction and compress it down to have very low depth. And one thing that we get as a result of our framework is a very simple proof of the main technical lemma in this prior work. It says that anytime you have two independent random unitaries, like U1 and U2, and you apply them so that they're overlapping on just a small number of qubits, just super logarithmic, just a little bit more than log number of qubits, then at least under forward queries to U1 composed with U2, you can't distinguish that from a Haar random unitary. So in general, this technique just seems to be an all-purpose way to reason about Haar random unitaries and prove statements like this using just elementary quantum information. Yeah.
Distinguishable means the definition in your previous slide, you have A matrix and
so yeah, here when I say indistinguishable in both of these, what I really mean is that you can take any quantum algorithm, actually any inefficient one as well, and as long as you bound its number of queries to be polynomial, then the resulting density matrix that you get, the density matrix you get on this side versus on this side, that those density matrices are going to be close in trace distance. And yeah, to be clear, the density matrix here, in this particular example, might not actually be trace 1 exactly, just because these unitary, a matrix where their random ±1 entries appropriately normalized is not necessarily unitary, probably won't be. But we show it's still close enough to being a trace 1 density matrix that these are close in trace distance. So it's kind of a, we've long had this intuition, right, that unitaries are, not just intuition, but there's formal statements about this, that Haar random unitaries are essentially unitaries of random Gaussian entries, random complex Gaussian entries. And this says that there's really nothing special about random Gaussians, that you can actually just replace those random complex Gaussians with essentially any sub-Gaussian random variable appropriately normalized, and you still get the same statements about indistinguishability from Haar random. Any other questions?
So previously you said you don't want statistical indistinguishability, but here you said you still in the end demand statistical as in trace distance.
Good. So the actual techniques that we prove, so I'll get into this in a little later in the talk, but this is a good point that, yeah, I started out talking about computational indistinguishability, and then over here I'm claiming that our techniques give you these like pure trace distance claims. And that's because of the way that we actually construct these pseudorandom unitaries is by proving a trace distance claim. We're going to prove that queries to a truly random permutation function Clifford give you some mixed state at the end that is close in trace distance to what you get from a truly random unitary. So the place where the computational guarantee comes in is because a truly random permutation and a truly random function on n bits is not actually something you can implement efficiently. And so in the end, you're going to have to instantiate these with cryptographic instantiation. So we're going to replace the truly random permutation with a pseudo-random permutation and a truly random function with a pseudo-random function. And then you're only going to get guarantees that are like about computational indistinguishability. But that's kind of a standard technique in crypto. And I'm basically not going to talk about that today. I'm just going to pretend that I can reason about the truly random case. And as a result, all the theorems are going to be about trace distance. Does that answer the question? Yeah, questions? Okay, so for the rest of these slides, so after a few more slides, I'm going to go switch over to the board. But before we do that, I just want to give like a high-level overview of what I mean by this compressed purifications technique. And so this is a very, very like elementary idea, and it just comes from some basic facts about purification. So one thing we know is that any mixed state rho on system H has a purification. I'll call it ket phi. And the purification is going to be on systems H and E. So H is always going to be the original system, and E is going to be some external environment. Okay? And if you have a purification, that means that if I trace out the E subsystem of phi, then I get back the original state rho. And these purifications are not unique. And this is like the basic fact that we're going to really exploit today. And in particular, like if you start with any purification of a mixed state, you can always apply like any isometry you want on the purifying side. So you can rotate the purifying side in any way that you want, and it's still going to be like an equally valid purification. And so the plan for how we achieve all of these results is like we're going to use this template where we're going to prove that a pair of complicated looking mixed states, let's say rho H and sigma H. I'll give the examples in just a moment, but just for now, imagine you're given descriptions of two different mixed states. And you'd like to show that they're close in trace distance. And the way you can do it with purification is, I mean, if it's actually true, is you can construct purifications like phi 0 and phi 1. And sort of all you need to do is find some way to rotate one purification so that it looks like the other purification. Right? You just need to find some isometry, V, that acts on the purifying side, such that when you apply this to the first purification, you get a state that is really close, let's say L2 norm or trace distance or whatever, to the other state. So I imagine this little template wasn't super helpful, because really the question is, how do you find this isometry V? Like that's really the whole problem here. And the idea behind this whole compressed purification technique is this general philosophy, which is that like the way that you find this isometry V is by trying to find a way to compress the purification. Like we're going to be in a setting typically where the sort of obvious purification that you write down is going to have an exponential size purifying register. This E system will be an exponential number of qubits. And if you try to find a way to compress this down to a polynomial number of qubits, that's typically going to be the way that you find this like magical isometry that lets you prove the statement you want. So this might be a little abstract. So the next slide, I'm going to do an example of like how you how you apply this, this approach. So this is kind of a toy example that's just cooked up for these slides. So define the phase state, psi sub f, to be the uniform superposition over all x. Oh, by the way, for today, I'm gonna switch between talking about like n-qubit states, like lowercase n qubit states, and state supported on capital N. So capital N today is always going to mean 2 to the little n. Okay. So define the phase state psi f to be a superposition over all strings x, where the phase in front is either plus or minus 1, depending on this the like x component of this vector f. So imagine f is going to be some vector in 0, 1 to the capital N, and that just dictates the phases of this state. So this is a binary phase state. And my goal, let's say, is to show that the mixed state you get when you sample a truly random function f, or a truly random string f, and you look at the mixed state ket-bra of psi sub f, I want to show that this state, this density matrix, is the maximally mixed state. Okay. So this example is actually really easy because you know, I am sure that some of you can see this. Like, if you just look at this density matrix, I mean, it's a capital N by capital N matrix. You can just go ahead and stare at every entry of this matrix and show that it really is the maximally mixed density matrix. You can show that like the on diagonals are some fixed constant, and everything off diagonal has expectation 0. But just for the sake of this example, pretend you don't know how to do that. And let's say you want to find a proof of this statement that does not require you to think about the density matrix at all. So what we're going to do is we'll start by writing down the like obvious purification of this density matrix rho. So rho, again, I'm sampling a classical random f and then outputting psi f. And so the natural way that you purify this state is you consider a subsystem, like another system E, where I'm going to store a superposition over all possible f's. Okay? And so of course, if I trace out this system, then the state I have left on the original system is just going to be my original mixed state. And what I'm going to do now is I'm going to expand this out. So I'm just going to plug in the definition of psi sub f. Remember, it's this up to normalization. And the kind of key step here is to just kind of rearrange this expression. And I'm going to do it as follows. If I take this phase here, the idea is I'm going to take all the coefficients that have anything to do with the ket f on the purifying register, and I'm going to rewrite the expression to group these coefficients, these f-dependent coefficients, with the ket f. So I'm literally just going to rewrite this -1 to be applied on this ket f. That's exactly the same thing. And once I do that, I can move the sum over f to be on the purifying side. I can write the sum over f over here. So hopefully you'll agree with me that these two expressions are equal. And so I'm just going to collect that over here. And now I'm going to call all of this stuff. So I have the sum over x of ket x on the original register in tensor product with like some state that depends on x. And let me just call that state phi x. And so I've rewritten my purification as the sum over x of ket x in tensor product with some state phi x. And now the idea is that we should try to, like, in order to understand this mixed state, I'm going to try to compress this n-qubit state phi x. And to do that, I'm just going to stare at it and see what it tells me. So remember that phi x is of this form, where I'm going to rewrite this f sub x. This is like the x component of this vector f. Let me rewrite that as the inner product of two vectors, f, and the vector e sub x, which is just 0 in every position except for the x coordinate. Right, so f inner product e sub x is just the same thing as f sub x. But now if I write it this way, I mean, we have a superposition over all strings f of ket f, and the phase in front is -1 to the f inner product something. And hopefully you recognize that as just the Fourier transform or the Hadamard of whatever that thing in the exponent is. So what we're saying is that this ket phi x state is really just up to a Hadamard. It's just the vector that is 1 in the x position. And so now it should be clear that these phi x states are all orthogonal to each other. Like for every x, the phi x's are orthogonal. And so you can just map these phi x states to ket x. So originally these phi x states are capital N qubits long. But what this shows is that like really the information they carry can be compressed down to log capital N, or like lowercase n qubits. And so what this means is that you can just apply an isometry, and you get that this is another purification of your state. And this you can recognize as just the maximally entangled state. And so this is, that means that this system is just the maximally mixed state. Any questions about this? Like the main result of this talk is just going to be like a slightly harder version of this slide. Are there no questions? I've lost everyone, or no questions that it's really clear? Okay. So for the rest of today, I'm going to move to the Blackboard. I'll leave the link for the paper written on the Blackboard. All right, so if you want to follow along with the paper, we just posted like a very preliminary draft today. It's available at this link. Okay. All right, so just remember that I'm going to keep this notation that capital N is 2 to the little n today, and I'll be talking about lowercase n qubit unitaries. And for the next like 45 minutes or so, I'm just going to be doing a proof of one claim, which is that this particular construction, this PFC construction of a pseudorandom unitary is like statistically indistinguishable from a truly random unitary if you only make a like bounded like polynomial number of queries to this ensemble. And then at the very end, I'll kind of like sort of step back from this proof and try to talk about kind of what this proof tells us about random unitaries more generally. Okay, so this construction has the following form. The output is going to be a random unitary of the form P times F times C, where P, I'm going to abuse notation, and I'm going to write capital P to denote both like a permutation on capital N elements, like a literal permutation, and the operator, like the unitary that applies that permutation in place. So in particular, I'm going to imagine sampling a permutation P from the symmetric group on N elements. So it's a uniformly random permutation on capital N elements. And then I'm going to write capital P to also denote the operator that maps every string ket x to ket P of x. And then I'm going to pick a random function f. So I'm going to switch between like thinking about a random Boolean function f. And so this is I'm going to think of this function as being defined by its truth table. So I'm going to think of it as sampling a random 0, 1 to the capital N. And I'm also going to let f denote the diagonal unitary that just applies this function to the phase. So it maps ket x to ket x, but it picks up a phase of -1 to the f of x. And finally, C is going to denote a random n-qubit Clifford unitary. And the only thing that I'm going to need about the Cliffords is that they form a unitary 2 design, which means that their second moments are exactly the same as the second moments of a Haar random unitary. So the construction is I'm going to sample uniformly random P, uniformly random F, uniformly random C, and I'm going to output P times F times C. And give me a moment to just and what we're going to prove is this theorem here that says that the state of an adversary, the mixed state of the adversary, when it gets a random PFC, is close in trace distance to the mixed state that you get when you feed it a Haar random unitary U. So just remember that this notation ket A with anything in the exponent, that refers to, we're imagining fixing a particular description of a quantum oracle algorithm which means fixing these unitaries A1 up to AT. And then I'm defining ket AO to be the state at the end of the execution of the algorithm. So this is just going to be, you start from some fixed state. I'm just writing 0 for simplicity. It doesn't really matter. Just some fixed state. And you're going to interleave applications of the adversary's fixed unitary and applications of the oracle. And I'm going to, it'll be easier to just use a shorthand product from I equals 1 up to t of O times AI applied to 0. So this product symbol means evaluating this from, I guess, right to left. Okay. As I've written it here, I haven't written down any ancillas, but in general, we should allow our adversaries to use any polynomial amount of ancilla space. And actually, for this trace distance claim, it doesn't even matter. They can have exponential size ancillas. It's all going to be the same. The proof is entirely, it's just completely identical whether or not you keep track of the ancillas or not. And so just to avoid having to write an extra register at every single step, I'm going to pretend that there's no ancillas, but the steps are all going to be the same. Okay. So the goal is to prove this trace distance claim. Okay. So before I do anything, I just want to give an outline of how the proof works. Because honestly, the proof structure is a little bit weird. So here's what we're going to do. What I'll do is, I think I'm going to define a state, a mixed state, rho superscript d. And this is going to be the mixed state that you get if the adversary is given a random p, a random f, and a random unitary sampled from d. So over there, this, I was letting d correspond to the Clifford group. But actually, I'm going to want to define this mixed state for any 2 design d. So not just the Cliffords, but this mixed state I can consider for any 2 design. And the reason I want to write down this mixed state sort of at this higher level of generality, or I'm not forcing d to necessarily be the Clifford group, is because when I write down this state, I can write down the 2 states that I'm trying to prove an indistinguishability between as both being states of this form. Right? In particular, if I instantiate D to be the Clifford group, that's going to be the view in the pseudorandom case. And on the other hand, the Haar measure itself, a Haar random unitary, is also trivially a 2 design. And if I plug in D being a Haar random unitary, well, then I claim that PFC, where if I sample C to be a Haar random unitary, that's just a Haar random unitary, by invariance of the Haar measure. Okay. So the claim reduces to, or what I would like to show is that this mixed state is, when I instantiate D to be a Clifford, is close in trace distance to the same mixed state, but where D is instantiated to be the Haar measure, or a Haar random unitary. Okay. And the way that we're going to prove this is we're going to show that for any 2 design D, as long as it's an exact unitary 2 design, there is always going to be one fixed purification that corresponds to this mixed state. So there exists a particular state we'll call the target state. It's a purification, so it's going to be on registers H and E. So I'll think of these as being systems on register H. And what I'll show is that this target state is an approximate purification of rho D, but for any D. So in particular, I'm going to show this trace distance claim, that rho to the D is close in trace distance to this target state after I trace out the E register. And the key point here is that this state, this mixed state here has no D dependence. And so by the triangle inequality, if I show that rho Clifford is close to this and also rho Haar is close to this, then these 2 are going to be indistinguishable or close in trace distance. Okay. So again, the key point here is I'm going to find kind of a simultaneous purification of both of the mixed states that I'm interested in. And that's going to show that they're close. And so simultaneous approximate purification. So only up to a small trace distance error. Yeah. Yeah.
So does this target state is unique?
Depends on what you mean by unique. I mean, I can always change the purifying register by any isometry. And also because the guarantee I'm asking for is only trace distance closeness, if I kind of nudge it in like any direction by like a little bit, it's also going to be true. But this target state that sort of makes the proof work is going to have some special significance that I will explain kind of at the end of the proof. Like for now, I'm going to work on just trying to construct this target state and prove this claim. But at the end, I'll talk about sort of what exactly is this target state and like what does it tell you about Haar-random unitaries.
Very nice question. So you're saying that there's no F and P that could somehow remove the Haar randomness from a Haar that you construct with the way you have rho D written there? You're constructing your Haar random unitaries as this rho D, and now D is being sampled at random, but there's no such like.
Oh, sorry. So D is a distribution.
Sure.
Yeah. Okay.
But there's
C is sampled from this distribution. Okay. And then this mixed state is a expectation over random P, random F, and a random sample from D. Okay, so can you repeat your question again? I was a little confused.
Just that when it's D and not C, there's no such like F or P that act in the way that you have written over here that would like.
Sorry, when you said it's D and not C, you meant C as in this or C as in Clifford's?
C is in the Cliffords.
Okay, yeah.
So there's no such F or P that would like remove the randomness somehow, like you accidentally create. By trying to build Haar randoms the way that you have there, you accidentally like extract some of the randomness out by some bizarre choice of F and P or something.
I guess I'm not totally sure what you mean. Like we're talking about, I guess I'm thinking about a mixture over the randomness of F and P. And so when you're handed the state, you don't actually know what F and P are. Like as far as you're concerned, like that like F and P could be lost, right? And I'm just saying like the resulting mixed state over the randomness of F and P, these are close. I'll
ask you.
Okay.
Good question at all. So
If anybody else is yeah.
Expectation value just by multiplying another matrix to the measure, for example.
Say that again.
Oh, you're averaging, so the expectation value, well, at least how I understand that, you know what? In the expectation value, you're averaging over the Haar random measure, so it doesn't matter if you multiply like one extra matrix, like.
Yes, exactly. Yeah.
So-
Yeah. So for any fixed P and F, if D were the Haar measure for any fixed P and F, that's definitely going to be what you the Haar random distribution. And then because P and F are sampled independently of the U, it's also true for a truly random P and F. And then the claim is that once you have this the randomness of P and F, that like you actually may as well switch the D to not be Haar random, but just any two design. Yeah. Okay. Great. Yeah.
Yeah, that's a nice question. So on the middle line,
Yeah.
you use the fact that you draw say approximately equal to draw from R, or that's a conclusion you want to apply.
Oh, this WT, yeah, it's want to show.
Oh,
Yeah,
yes.
sorry. Yes. The goal, like, I just wanted to say that like we want to prove that theorem, and I'm going to sort of reduce proving that theorem to proving this claim here. Because once we prove this, it's going to imply this claim. And well, this claim is a rephrasing of the theorem. Like this, the way that I've defined rho D, this is supposed to be, this is going to correspond to the mixed state in the pseudorandom case, and this corresponds to the mixed state in the Haar random case. This one, like by definition, is equal to the mixed state in the pseudorandom case. And this one, you have to squint for a second and realize that because of the invariance of the Haar measure, if D is the Haar measure, then you can, doesn't even matter that P and F are there.
The essential part that the target state does not depend on D.
Exactly.
Okay.
Yeah, that,
So the same equation applies for Haar.
yes. The claim is that, yes, no matter what two design you use, there is always like a shared purification or shared approximate purification. Yeah. Any other questions? The next maybe 20 minutes or so are really going to hinge on this making sense. So please ask questions now if you have them. Should I perhaps get like a thumbs up or thumbs down on kind of, this is all, okay, good. Yeah. Is this the right board? Okay, yeah. So what I'm actually going to do is, well, as I suggested, I want to come up with like these compressed purifications that are going to help me understand these mixed states. And turns out like the way that I'm going to do that is I'm only going to focus on the randomness of P and F. And I guess like roughly the intuition here is that P and F are exponentially long. Like P is a description of a permutation, F is a description of a random function. They're very long. Whereas C is this like random Clifford, it's in some sense like already compressed. And so when I apply this compressed purification technique, I'm only really going to use it to compress the randomness of the permutation P and the function F. And the Clifford is going to play a different role in the proof, or the two design is going to play a different role in the proof. Okay. So what I'm actually going to do to understand this mixed state rho D, I'm going to rewrite rho D. Right, this is rho D. I'm going to break up, I mean, rho D has expectations over 3 random things, the P, the F, and the random C sampled from this distribution D. And I'm going to bring that expectation to the outside. And on the inside, I have this expectation for a fixed choice. Like when I'm looking at just the inside, I have a fixed choice of the unitary C. And it's just a truly random choice of P and F. So I'm often just going to drop like how these are sampled, but whenever you see expectation over P and F, the P is sampled as a random permutation and F is a random function. Okay. And I'm just going to stare at this mixed state in the middle. So this is a mixed state that is, I'm going to call psi C. Okay. This is a mixed state for a particular choice of C. And my goal for now is going to be, my plan for now is I'm going to fix the choice of C. It's going to come back later in the proof. But for now, I'm going to fix it, and I'm just going to try to like get some insights from purifying this state psi C. Okay. So to purify this state, let me first just remind you that this ket APFC, this state can be expanded out as follows, right? This is just the definition of the ket A states. It's that you start from a particular fixed state ket 0. And then you just, from steps 1 up to T, you interleave applications of the adversary's unitary with applications of whatever is in the exponent. So this is a PFC. Okay. I'll need this again. All right. So let's see, maybe I want to go to this board actually. Good. So my goal here is to purify that mixed state psi C. And I claim that the natural or obvious purification of this state is the following state. I'm calling this ket phi. So remember that ket phi is the purification of the adversary state for a random choice of P and F. Okay. And so this is the adversary state. And this is to write down the purification, I'm just going to consider a superposition over all choices of P and F. And I'm going to store this P and F on some external system that I'm calling E. Okay. So hopefully it's clear that this is this is a valid purification of my mixed state psi C. Because if I measure this, then it's going to collapse to a truly random choice of P and F. And this is going to be the correct mixed state. Also, for all of the steps that I'm about to do, there's going to be 3 more blackboards. This C is going to stay the same. And the expressions are already kind of big already. So I'm just going to stop writing this. But I'll put it back later. Okay. So either you can pretend this is not there, or you can redefine the AI to actually be C times AI. But for now, I'm just going to ignore the C. Okay, so the first thing that I'm going to do, and this is, if you remember the proof from the slides, the intuition here is that I have this ket P and ket F on the purifying register. And what I'd like to do towards finding like a more like insightful way to view the purification is I want to expand out this expression to move all the terms, all the coefficients that depend on P and F to the purifying register, and then kind of just understand like what's happening on the purifying side. Okay. And so to do that, I need to actually like plug in what are these P and F operators here. Okay. And for that, I've pre-computed it here. What is the P times F operator? Well, P, remember, is just the permutation being applied in place. F is just the diagonal unitary that applies F in the phase. And if I expand this out, well, these x's match up. And so I'm just going to get a sum over all x. And what it's going to do is it's going to map ket x to ket P of x. And it's going to pick up a phase of -1 to the f of x. And because my goal is to move all the coefficients to the purifying side, I want to move all the terms that depend on P and F to the purifying side. It's going to be helpful to rewrite this expression in such a way that I can do that. So I'm going to rewrite this expression so that instead of having P of x written inside the ket, I'm going to move it to a coefficient. So I'm going to sum over all y's, and I'll have a ket y over here. And I'm going to represent ket P of x as just this like delta function, delta sub P of x equals y times ket y. Right, so hopefully this is just clear. This is just another way to express ket P of x. But this is going to let me move these coefficients over later. Okay. So let me plug this in. And if I plug in this expression into here, all that happens is this red thing I underlined here, this PF, is going to blow up into this slightly scary looking expression here, but this is just the expansion of this operator. Right? So it's writing this operator as a sum over all of the entries of this matrix times whatever that coefficient is. All right. So the next thing I'm going to do is, again, following what I did in the slide, I want to move all of these coefficients, the ones that depend on P and F, I want to move them over to being on the purifying side. So what I'll pick up if I do this, I'm going to have one of these delta P of xi equals yi for every I from 1 to t. And so I'm going to group that with ket P. And just for shorthand, instead of writing this product from I equals 1 to t of these constraints that P of xi equals yi for every I, I'm just going to write that as delta of P of like this x vector is equal to this y vector. So my notation is going to be that x vector is equal to x1 up to xt, and similarly for y. Okay. So that coefficient shows up here, and there's one other coefficient that I have to take care of, which is the -1s. And the -1s I'm going to move over here. And because I'm multiplying t of them, the exponents are going to add. And so I'm going to have -1 raised to the f of x1 all the way up to f of xt. Okay. The thumbs up, thumbs down, head nods. This is all clear. Okay. And then the one last thing I'm going to do to this expression is actually two more things. I've moved all these P and F dependent terms to the purifying side. So now this sum over P and F. Yes. Oh, I got rid of it. It's really there. I just didn't want to write it. There's a lot of symbols. You either can define the AI to be like AI prime, which is equal to C times AI. Okay. Or you can pretend I wrote it there. Yeah, the board is finite length and so, okay. Oh. Okay. Yeah, definitely remember that like later it needs to go back in here. So whenever you see this expression, you could think of like a phantom C being there, but it just doesn't matter for all these steps. Okay. Good. So the last thing I want to do is these are the only terms that depend on P and F, so I may as well just move this sum to being over here. And it's also going to be a little bit more illuminating to write this expression by exchanging this sum and this product. Okay, so I'm going to exchange the sum and this product, and I'm going to sum over all x vectors, all y vectors, in capital N to the t. And now I have this product, and now it's a little simpler of an expression. It's just like it's interleaving these AIs with these ket bra yi xi. So it's like it's mapping xi to yi in every single at every step, and you're summing over all possible ways to do this. So what's really happening is I'm taking the purification of the adversary's state and writing like a Feynman path decomposition of this purification. Right? Because what's happening is like there's T unitaries A1 up to AT being applied. And then I'm sort of regrouping the purification so that I look at the terms and like I'm going to regroup this purification so that I'm summing over all possible Feynman paths. Right? So this is like for every x vector, y vector, that corresponds to like the path where you go like x1 to y1 and then x2 to y2 and so on. Right, like that's what's happening over here. Okay, and I'm going to let like ket a sub x vec and y vector be like this particular state corresponding to this path. And what this way of rewriting the expression gives me is sort of a way to keep track of, well, in every possible path that the adversary state can take through these t steps, like what happens in like what is the corresponding thing that happens on the purifying register, right? And my claim is that actually what happens to the purifying register is it's going to be recording some information about the path. Okay. So in particular, whenever you go from like x1 to y1, over here you're going to pick up on the superposition of f register, you're going to pick up like a -1 to the f of x. So let me say in orange maybe, when I go from like xi to yi, like just imagine like at one step when I go from xi to yi, like what's happening? Over here, I'm multiplying in a -1 to the f of xi. Like I had the superposition over f's, and then it picks up this phase. And then over here, I multiply this weird delta function, p of xi equals yi. Okay. So that's what happens at every step here. So, and the intuition is that like the way to be thinking about these queries to this random P and F in this purification view is that there's a external purifying system that is like recording or picking up some information about the various paths that the state can go down. Okay. And now I want to be a little bit more precise about like what information is actually being recorded on the purifying side. Okay. So it's going to turn out like it's actually not enough to, it's not actually recording the full path. It's only recording some partial information about the path. So let me reveal one more board. I guess at the same time as like trying to understand like what information is being recorded, this is really going to be our way of compressing the purifying side. Okay. So again, I'm calling this state AXY, and then the state on the purifying side that's like accompanying this phi XY. And I claim that there's a way to really understand like the information contained in phi XY as follows. For this, let me just define the notion of a set state. So I want to consider states that correspond to a set as follows. So if I have a set of elements z1 through zt, and the corresponding state z1 through z, like for that set, is going to be the superposition over all permutations of the elements of that set. Okay. So this is just like one way to like represent a set, because a set like contains the elements but doesn't contain any particular ordering of the elements. So this is one way to represent a set. And it has a property that, like, when I write this, I really mean that, you know, if you have two different sets that are like not equal, then their inner product is 0. And if they're equal as sets, then their inner product is 1. Okay. Now the claim is that there is an isometry, just a one isometry V, that has the effect of compressing this information, this phi xy state. And it doesn't actually do it for all choices of x and y, but it does it for a large fraction of them. In particular, if I define n to the t distinct, this is going to be the subset of like t tuples that have all unique elements, like x1 through xt are all unique. Okay? So there's no collisions in the tuple. And if you, by the way, just for intuition here, like remember that capital N is really, really big. And in comparison, we should think of this little t as very small. So you have a t tuple of elements where each one is sampled from capital N. Intuitively, you would expect most of them to not have collisions. This is like a birthday bound thing. Right? So I'm saying, like, for a large fraction of these x's and y's, there's an isometry that maps this state, phi xy, to a state of this form that is really just recording the set of ordered pairs x1, y1 up to xt, yt. So, sorry? Nope. That's not, yeah, you don't. Yeah. You do. Yeah. Yeah, I'll show you in a sec. Yeah. Yeah, it feels like it.
Otherwise,
Yeah.
it's not sitting where it should.
Yeah, it feels the same, but it's actually you do need the F, it seems. Yeah, or at least the way that I know how to prove it. Yeah. Yeah.
What's the mean?
Oh, so that's what this line was for. I was trying to say here, like, okay, usually, like, yeah, it's weird to write these like sets thing. But when I write something inside the ket, I just mean that I want to associate like if there's a mathematical object inside the set, then inside the ket, then I want to say that two kets are like or two vectors are orthogonal if that set is the same, or if the set is different. So I'm saying like this is like a vector where it's like orthogonal anytime you have two different sets of ordered pairs. And they're parallel if they're the same set of ordered pairs. So what I mean is, like, if you have, yes, yeah, that's what it's saying. Yes. So it's saying if you took the path x1 to y1 on your first query, and then x2 to y2 on your second query, versus if you took x2 to y2 versus x1 to y1 on your second query, it's saying that these two produce exactly the same state in the purifying register. Yeah, that's what that notation means. And like the intuition is like just because of what's happening here, you're just multiplying on a coefficient onto the purifying side every time you traverse like one step of the path, right? So if you're just multiplying things in, it doesn't multiplication is commutative. So it's not going to matter what order you're multiplying these in, as long as you're multiplying in the same elements.
Mutation, different paths will produce orthogonal vectors.
Yes, exactly. But if you,
It's much less intuitive than the other.
yeah, exactly. So, right, if you go down a particular path, then on the purifying side, it is storing your path up to order. That's the key claim here. Provided you are going down a path of all like distinct elements, like none of the x's that you visited or the y's that you visited overlapped with each other. And that is what this is saying. Yeah.
Just count the number of paths traversed instead of why even write them down at all? You don't care about x1 to y1, x2 to y2, etc. Like, why not just count the number of paths and apply that phase?
Sorry, what do you mean by why not? In the sense, like, I guess this is just like, I'm claiming that this is a fact about the state that I wrote down. So are you proposing like a different state or a different isometry or?
Down this state with its set and these individual transformations, x1 to y1, x2 to y2, and just writing down the number of queries you had and applying an overall phase that's -1 to the number of queries. That's my question.
The order doesn't matter.
Right, then it's just the number of times that you're actually querying the oracle. What am I missing?
Are you proposing that I prove a statement like this, but where this state is different?
I guess where that state's just a number, it's the number of times that you queried, and that's giving you that.
Oh, I guess I don't. What does it mean for a state to be a number?
Oh, no, okay, so that doesn't make sense. What I'm saying is it's the -1 to that power that's right above your head right now. That is coming from just the number of queries, right? Or am I wrong there?
There's a superposition over all F. And so that makes it different. Yeah, because for every different F, this is like a different number that you record, right? So actually, like what I'm about to argue is that what is being stored over here is actually going to be the set of x1 through xt. Like when you look at this in the Fourier basis, that's what's going to happen. Does that clear it up? It was like just this thing that made the difference, right?
Yeah.
Okay.
Set, it's the actual.
Yeah. Okay. All right, so let me just give, like I'm not gonna do a full proof of this or anything, but let me just give some like intuition for why this is true. So remember, I'm trying to show like this state phi xy, which is of this form. Like why is it the case that from this state I can recover this set of ordered pairs xi yi? And the first step is to notice that if I look at just this part right here, I remember that I can write f of x as equal to f inner product e sub x. And as a result, this state over here is, I can rewrite it as -1 to the f inner product ex1 up to ext. And this here is just the Hadamard, the Fourier transform of ex1 all the way up to ext. And so this here, this is a vector in 0, 1 to the n, where most of the positions are 0, and the only ones that are non-zero are the positions that correspond to x1 through xt. And so really this is like a very long vector, but it can be compressed in the sense that the information that it contains is, you can just say, where is this vector non-zero, right? And because these x's are all distinct, like there's not going to be any cancellations here. It's all done mod 2, but there's no cancellations here because the x's are distinct. And really, like this is just equivalent to, or I can apply some unitary to this, or isometry, that's going to map this to the set x1 up to xt. So that's the first thing I can do. I can extract the set of x's from this part. The second thing I can do is I can read this p, like I can apply an operation that's like controlled on this p, looks up what every x is mapped to under p. Right, so I can apply the operation that maps x to p of x, or it's going to map x to the ordered pair, x comma p of x. And applying this operation, I can map this part of the state to the set of ordered pairs, x1, p of x1. Let me write it as I. Okay, so again, I start with having the set of all the x's, and then I'm going to take every x and map it to the ordered pair x comma p of x. But remember that every p that's in this superposition, like we know that p of xi, we know that p of xi is equal to just yi. Right? This is precisely like what this constraint is encoding. This delta function ensures that every p that's in the superposition maps xi to yi. And so that allows me to transform this state into the set of xi, yi's. And finally, once you have this set, the last thing you need to do, so I got this set like on this register here. The last thing I need to do is uncompute this register. But that state on the P register is a superposition over all permutations P, such that xi is mapped to yi for every xi, yi in this set. So this is like a set of kind of like, particular, it's like a partial truth table for the permutation. And using this, you can like uniquely specify that superposition, and therefore you can uncompute it. So yeah, and like once you have this, you can uncompute the first register, and that's it. So that's how you get from phi xy to this set of ordered pairs. Okay. Any questions? I went a little bit fast, but this is the, I guess, the key like compression step in this proof. It's showing that you initially start out with these states, which are n or even n log n or something qubits long, because they contain an entire description of a permutation and a function. And then over here you get these like set states that are only 2 nt qubits long. Yeah.
Or superposition, but a factorized state.
By uncompute, I mean you delete it, like you map it to the 0 state or something. Like, from the 0 state, I can prepare a uniform superposition over permutations. I claim that with a little bit more work, you can prepare a uniform superposition over permutations that satisfy a certain set of constraints. And you can like therefore reverse that whole process.
Okay.
Yeah, any other questions here? Yeah.
Then this somehow by saying that you consider the purification as an operator X acting on your first system, then the identity on the maximum entangled state at last. And then you move part of your X to the second register. Is this somehow a way of understanding how you move your P and F, part of it to the second part of the P?
I'm not sure I follow that. Do you mind saying that again? Okay. Yeah, we can try to take it offline. Okay. Good. So, all right. With everything that's happened so far, let me just kind of recap like where we've gotten to. So our goal was to understand this like psi C state. Right? That was like this mixed state over the random choice of P and F. And what we wrote down was this purification. I'm going to reintroduce this C now. It's going to start mattering in just a moment. So I wrote down this purification phi that really should have had a C there all along. And what we just saw kind of suggests that you want to like separate this purification up into 2 parts. One part where you can compress the purification, where this isometry applies. So that's going to be the part where these x's and y's are all like unique. They're all like a vector of distinct tuples. And the other part I'm just going to call the bad terms. These are everything else that we don't know how to handle. Okay. And it turns out these 2 terms are orthogonal to each other, and they can actually be like perfectly distinguished by just looking at the purifying side. And later we'll be able to argue that you don't have to worry about the bad term. So let me just focus on the good term for now. Remember, the good term is it's the superposition over the x's and y's where you've restricted to these like distinct paths. And for these terms, we're allowed to write the purifying register as just recording this set of ordered pairs, this xi, yi set. And now I'm at a point where I can define this target state. So if you recall, like the goal of this proof, or the endpoint of this proof was I'm going to produce a state target that is like an approximate purification of this mixed state for any like 2 design D. And my target state is going to be almost the same as this good state over here, except that I'm going to sum over all x's. Okay. So again, like this state here is only summing over the x's and y's, where the tuples are all distinct elements. And I'm just going to make one tweak to it and say that I'm going to sum over all the x's. And I will still keep the same restriction on the y's. Okay. And I claim that defining this target state, like this particular state, it's going to have some like truly like magical properties that'll just make the rest of the proof work. Before I go on, now is I'll pause for questions on what's happening next. And so, yeah.
What did you mean by the bad state?
Good. So I have this state I see. It's like a purification, and like my purification is I mean, it's a sum over all these like x vectors and y vectors of like some path state in tensor product with like some state on the purifying side. And the claim was that like I have a way of understanding what that purification state is when x and y are like in this distinct restriction. So I'm going to say that like I'm only going to focus on the parts where I know how to do the compression, and everything else I just ignore it. Hopefully, like we'll somehow like try to take care of it later. Yeah. So that's the idea.
Why the target you want to remove the distinct
X? That's completely unclear at the moment, but I'll say it in yeah. It just turns out that making this change is going to cause like magic to happen in this state. Yeah. Because again, like really the thing we need to take care of or make use of, we've never used the fact that C is a MER2 design yet. So I claim that like the way to make use of this fact is to define this state, and I'll show like what happens in just a moment. I have about 10 minutes left, so I'm gonna move a little quicker. But any questions on like what the plan is or stuff so far? Okay, so all I need to do is write out this target state. So I'm going to do that. I think. So it's a sum over all x's and a sum over all y's that are distinct. Over here, I have this product from I equals 1 up to t of yi xi. There's a c over here. This is going to matter. AI, which is what the adversary does, all on 0. And now this is in tensor product with this set state over here. And I'm going to write this set as this superposition over all permutations of the elements of the set. So instead of just writing it in that compact form, let me write this as the following. So a sum over all permutations of t elements so this is just the target state rewritten. Okay. And I've rewritten the set of x1, y1 ordered pairs as a superposition over all these permutations S pi, where remember that S pi, this is just like the swap operator. It's going to swap the subsystems according to the permutation pi. Okay. So here's the magic claim. It's that I claim that this expression is exactly the same as if I delete the C over here and insert it over here. So particular, the way the state is defined it's such that this target state with C is equal to C to the tensor T applied on the E register, actually like the X part of the E register, applied to the target state without any C. So again, like we want to handle this Clifford or this unitary C that's being applied before every single query. And I claim that if I have this Clifford here, it's going to be like the form of the target state makes it such that this Clifford is actually like invisible to the adversary, in the sense that there's, I claim that that applying this here, it's equivalent to removing it and moving it to over here. And this is that now it's on the purifying register. It's going to be invisible to the adversary. It's a unitary on the purifying register. And the reason this is true is because of a really simple identity. It's actually like the cyclic property of trace. I'm using this identity over and over. That if I have a sum over all x's and I have a C applied here, it's exactly the same as that same expression where the C is applied on the other side. Like this is just like a relabeling argument, or you can think of it as this is just the trace. It's a change of variables, yeah. Yes, yeah. And that's why I did this definition change where I switched from the summing over the x's that are indistinct to the summing over all the x's, because that is the thing that allows me to do this argument. Like because I'm summing over all of the xi's, like I have a sum over x1 through xt, summing over all the x's, that is what allows me to like identify this expression in the middle of this guy and move this Clifford over to the other side. So once you have this property, it basically completes the proof. So let me explain. Turns out this target state here, one more thing I'll need is that this target state has unit norm. So this is not obvious at all, and I'm just going to ask you, like, take me at my word for this. So what's going to happen is the following. And I'm just going to sketch this because I'm basically out of time. But it's the following. We're trying to understand this state here, this rho D state. And we're writing it as this expectation over C from D, and then the size C state in the middle. And my claim is that you can basically replace this size C, or you can replace the size C with its purification, this phi C state. And this phi C state, or when you trace out the E part of the state, this phi C state you can write as like sort of a linear combination of this target state together with some other junk. And who knows like what that other junk is. But the claim is that when you randomize over the choice of C, that the target state kind of takes up like the majority of the weight of the state. So particular, when you have this random C, it shows up here, and then it jumps over to this side of the state. And now what's happening is like you're applying a random C to like the purifying register of your state. Okay. And what's the difference between the target state and the part of the purification I can understand? Well, it's the x's on which there are collisions, right? That's the only difference here between the target state and this part of the purification. But now, if I try to sort of restrict myself back to the x's that have no collisions, I claim that this like random C sort of gives you that for free. That if I apply, and this is like a key fact about two designs. Like this is the only place in the proof where the fact that it's a two design matters. Which is that if I apply a C sampled from a random two design, or C sampled from a two design, and I apply C to the tensor T, the resulting state is going to be such that all the x's are going to be distinct with high probability. Okay. So this is a lemma from a prior work of Mecker, Premba, Sinha, and Yuan, that you take any state and you apply c to the tensor t to it. The result is something that's almost entirely supported on on strings of distinct elements. Okay. And so what that says is that the target state is really close to this target state is really close to this good state here when you randomize over the choice of C. And finally, because this target state is norm 1, that says that there's nothing else left in the state. There was all these bad terms that we didn't know how to take care of, but because the target state has unit norm, there is kind of nothing left in the state that the rest of the density matrix has to have a negligible contribution. Yeah.
Here you're saying the lemma saying you apply the two design and most of the term in the purified part is a distinct x, right? Are distinct x.
Yes. Yeah, there's a relationship between the target state and this good state, which is basically that the target state is equal to the good state is equal to the target state after you project the x's onto the distinct subspace. And what this is saying, yeah.
Compared to all x choices, right?
It does, except that the adversary can pick the x's. The adversary can pick its behavior to try to put more weight on the x's. The adversary can query the same unitary on 0 twice, and it can put a lot of weight on the x's. Right? It's not that the adversary picks sort of how much weight it can place on every xi. And so the whole point of this randomization by the C is to say that once you do this, the adversary no longer has the ability to kind of access the parts of the purification that are hard to understand. It can only place weight on the x's that are distinct.
Okay.
Okay. So I'm basically out of time. I want to say one last thing in a couple minutes, but any questions? That would be a good time. The last part of the proof was a little fast, but I mean, basically the idea was that you purify the randomness of the P and the F, and that gets you to a state that it's almost easy to understand, except for the fact that there's these collisions in the x's, and it's basically the choice of the random Clifford comes in and prevents you from having to worry about that part of the state. Okay, say one last thing. So there's one more way to think about this target state. Remember, this is the state that I'm claiming is close to the view of the adversary when it queries a random unitary. It's also the result of applying a particular linear operator that I'm going to call W. And W is a linear operator that does the following. It's going to map X on the adversary side together with R. And R, I want you to think of this as a set of ordered pairs. And I'm going to consider the linear operator that does the following. It maps XR to a superposition over all elements Y that do not appear in R, or in particular, they don't appear as the second coordinate in an ordered pair in R. Together with Y, R union is ordered pair XY. So this is a linear operator. I claim it's actually an isometry. It preserves norms. And the claim is that anytime you have an algorithm that queries a Haar-random unitary, you could instead imagine an algorithm that queries this isometry W instead. In particular, you consider the state of an algorithm AW, or you consider this state where I have a product from I equals 1 up to T of W applied with AI. All this. And the claim is that this is a close approximation of what it means to apply a Haar-random unitary. So this W is this linear map that acts on both the adversary side and the purifying side. And if you look at the state you get from implementing all your Oracle queries with this linear map, I claim that this is exactly equal to the target state. So this is another way to understand this state that came out of the proof. And so the way that we get a lot of our other results, like these applications or these new statements about Haar-random unitaries, is to say that whenever you want to analyze a quantum algorithm that queries a Haar-random unitary, you can instead think about this linear map, which is just taking a string x, mapping it to the superposition over all y's, and just recording that ordered pair on the purifying side. So we call this the path recording oracle. And it gives you a way to kind of like prove statements about Haar-random unitaries without having to break out the Weingarten calculus. And instead, you can just focus on analyzing like this elementary linear map. And so, and kind of the way that you discover this linear map is by like going through this PRU proof. Okay.
The targets is still depends on definition of C, right?
Oh,
the target is independent of choice of C.
Yeah, sorry. I guess I forgot to say this, but once the C is over here, it's kind of doesn't matter anymore. You can get rid of it. And the reason is that C commutes with S pi. Like if I have C to the tensor T, this commutes with swapping the systems. Like I apply the same unitary to every system. Doesn't matter like how I permute the systems. And once you commute this C over here, now it's just a unitary that's acting on the purifying side. And so you can just remove it. Yeah. So the target state is like the state that is like sort of invariant under unitaries. And the claim is that the way to like explain this target state rather than like writing out the full expression is just imagine that at every step you query this linear operator that's sort of recording all possible paths. So I'll probably wrap up here, but maybe one quick question before we, yeah.
So the step, okay. So the step that you change the X choice from the distinct one to the non-distinct one is because the two design C may acting on the all the X is equivalent to the distinct one.
Yeah, I guess, sorry, I have these two states, phi good and the target state. And the relationship is that the good state is what you get if you take the target state and you just project the x's onto the distinct x's. And then
You do with C.
good. So what happens is that like I basically want to argue that this projection step has almost no effect on the state. And the claim is that because of the form of this target state, the C kind of passes through the state and shows up on the purifying register. And it gets applied to these registers that you're going to apply this projector on. And then I'm claiming that there is a special fact about two designs that says that if I randomize by C to the tensor T, and then apply a projector onto these distinct strings, that projector has basically no effect because you're already in that set of distinct strings. So then the claim is that actually the target state is close to this good state after you randomize over the C. And yeah. Sorry, I should have said this. I ran out of time a little bit, but that's kind of how all these pieces come together. It's that, yeah.
But in this statement, it's crucial that T is much less than N, right?
This works up until T is like square root of capital N. Or at least after that, like you get no more, you get trivial guarantees after that point, I think. So basically up to the birthday bound.
It's like research.
Yes, yeah. So this is like a way to sort of approximate moments of Haar-random unitaries.
Norm 1 is exact.
It has what?
Norm 1.
The norm 1 is exact, and that's actually pretty useful for this proof. Yeah, because it's an isometry. And so if you are applying the isometry at every step, you'll keep your norm.
Okay, so I think thank you very much for the talk.